Welcome to this video lecture. We're going to talk about the Karman momentum integral equation today. The Karman momentum integral equation is a semi-empirical method for analyzing boundary layers. In the last lecture, we talked about laminar boundary layers, namely the Blasius solution. That's an analytical solution to the boundary layer equations. But we had several restrictions on that solution. Number one, it had to be a laminar flow and there's no pressure gradient, so it's flow over a flat plate. You know, not every situation is like that, so we need some tools to be able to look at flows with pressure gradients, turbulent boundary layers. We need a little more flexibility. Unfortunately, there aren't any known analytical solutions for turbulent boundary layers or just arbitrary flows over curved surfaces and things like that. So we need to rely on some sort of empirical method. And the Karman momentum integral equation is that method that's commonly used. It's semi-empirical because there's some theoretical parts to it as well as some experimental parts. And I'll describe that as we go through the lecture today. Let's go ahead and look at the screen. So the picture here is showing the back half of a car. You can see sort of a winglet on the back part of the car here. But what I really want to focus on are these things right here. These little triangles are known as vortex generators, and you can see some smoke being generated on the surface of the vehicle here. So these little black things are generating some smoke, and then they come out and you see they interact with these vortex generators and then kind of follow down along the back end of the car. The purpose of these vortex generators is to control the boundary layer. They do what's known as re-energizing the boundary layer. As you already know, the boundary layer has low momentum air to it. Let me sketch this out for you. So here's our boundary layer, has this kind of profile. Close to the surface down here, the boundary layer has a small velocity and thus small linear momentum. And this low momentum air, it turns out, as we'll see in a couple of lectures, doesn't flow very well into higher pressure regions. So if we had a high pressure in this region, so high pressure, sorry for the abbreviation there, then this flow won't go into that high pressure region very well. You can imagine that if you have small amount of momentum here and you have pressure pushing back on it, that fluid won't want to move into that region very easily. High momentum fluid, however, may be able to push further into that high pressure region just from its momentum, right? It has a high momentum, it can push further against that pressure gradient. But low momentum air doesn't very well. And that gives rise to what is known as boundary layer separation, a topic we'll cover in a couple of lectures. So what the purpose of these vortex generators is they swirl the flow around. You can sort of see that they'll swirl the flow around here, and they'll take this high momentum air and mix it in with the low momentum air next to the surface, and thereby re-energizing or putting more momentum into that boundary layer flow very close to the surface. And once you have higher momentum, then you can move further into a high pressure region. And so that's what the purpose of these vortex generators is they'll put additional momentum into the flow right here. When the back half of the car kind of moves away, you know, down the rear windshield and over the trunk, that turns out to be a high pressure region. So let me kind of sketch this out over here. So here's this car shown again. The flow's going this way. And what normally would happen is this would be a high pressure region back in the back part of the car. Flow's going from left to right. So that would be a high pressure region in the back half of the car. Normally the boundary layer would separate and you'd just get flow going this way. And so you'd have a large low pressure region, I should say this is not high pressure, but the pressure is increasing in that region. So what ends up happening is the boundary layer can't make its way into that increasing pressure region. We call this an adverse pressure gradient, and the flow separates. But if you have these vortex generators, the flow has more momentum to it, and it can actually follow the contour a little bit better if you have the vortex generators because you put more momentum into the boundary layer. We're going to talk about that topic in detail in a couple of lectures. I just wanted to give you a little preview here, and it's kind of a neat picture here related to boundary layers. By putting these vortex generators on here, you can actually reduce the amount of drag acting on the car and improve gas mileage and such. So it's kind of a neat idea, and it all has to go. The function of these things really comes back to the way boundary layers work. Okay, so anyway, let's go into our material for today, the Karman momentum integral equation. It's named after Theodor von Karman, who proposed the idea. And again, it's a semi-empirical method. We're going to go through the theoretical part first, and then I'll tell you where the empirical or experimental parts come into play. The derivation I'm going to go through, you don't need to know the details of it. I'm just showing it to you so you know where it comes from. But it uses all the tools you've already learned in this course. It's going to use the linear momentum equation and conservation of mass and Bernoulli's equation. So we're going to use all three of those tools in the analysis. So the idea is this. We're going to take a look at a small portion of the boundary layer. So here's a small control volume, small in terms of distance along the surface. So it's a little dx along the surface. The flow is going from left to right. And the boundary layer on top is at the boundary layer thickness. The control volume at the top is at the boundary layer thickness at the inlet. And then, of course, the boundary layer could change over this small distance dx. So here's the thickness of the boundary layer at the outlet. And you can see that the boundary layer thickness changes by a small amount, d delta. So here's the flow coming in with its velocity profile. Of course, in the outer flow, the velocity is capital U, and we'll just say that it stays at capital U in the outer flow. Flow can come in through the top of this boundary layer, and it'll have the outer flow velocity capital U as it comes in. Because remember, outside the boundary layer, the velocity is capital U, so it's going to be coming in here. The dashed line on top just follows the boundary layer. It's not a streamline, so we can have flow crossing into our boundary layer here. And then, so this is what the flow into and out of the control volume looks like. Now let's go ahead and show a free body diagram of that same control volume. So this is the same control volume. Still has a distance dx here. Along the bottom we'll have the wall shear stress times dx times unit depth in and out of the page. So this is the force on the bottom. On the left face there could be some pressure there. We'll just call it P. So that acts P times the height here, delta, times unit depth in and out of the page. Over here, that pressure force could change a little bit, so it's the pressure force that we start with on the left-hand side, plus how that pressure force can change with respect to the x position, times how far we've moved to get here, which is dx. So this is that, and actually so this is that Taylor series approximation. And then on the top, there could be a pressure force as well. Because since if the pressure is P here, and then the pressure is P plus dP over dx times dx, so that it could change, then the pressure over on the top will be kind of the average between those two. It'll be exactly in the middle because it's such a small control volume. So the pressure up here is P plus dP dx times 1/2 dx because we're right in the middle. That's the average. And it'll be multiplied by this little height here, acting in it's the projected area in the x direction. So this is just d delta. There should be a d there. Okay, so hopefully you see that on the top surface. We're just drawing the forces in the x direction, and on the top there'll be a pressure force acting over this projected area, d delta. And the pressure on the top will be this Taylor series approximation for right in the middle of the control volume. So that's why we have a 1/2 dx. So this is where, on the left-hand side, we're just showing what's happening with the flow, and on the right-hand side is the free body diagram. And then what we're going to do is apply the linear momentum equation to that, as well as conservation of mass. So I guess we're going to start first with conservation of mass. So here's the conservation of mass statement. Here's the mass flow rate in through the top. Right here, we'll just call it m dot top, and it's negative because it's coming into the control volume. Here's the mass flow rate coming in at the left. That's just along this surface. Let me highlight some of these things so they're easier to see. So m dot top is coming in right here. In at the left, this one is what's coming in over here. And then the one that I'll do in green is the one that's going to be going out there. That's this whole thing. And what's going out, it'll be the mass flow rate that's come in on the left over here, plus how that mass flow rate changes with respect to x times dx, because that's how far we move from that side to that side. So this is that Taylor series approximation. So then we can simplify that, and we'll get this expression for the mass flow rate in from the top. Now let's go ahead and do the linear momentum equation in the x direction. That's this expression. So the forces in the x direction on the control volume will be the pressure force on the left. That's this one right over here. Then we have our, let me shrink this down. guess that's, there we go. Then we have our pressure force on the right-hand side, that's this one. Then we have the pressure force on the top, that's right up here. And then we have our shear stress force on the bottom right down there. Okay, so those are the forces. There's no body force, we're assuming in the x direction. And then we have our momentum fluxes. So we have the momentum flux coming in through the left, going out through the right, and then there's a momentum flux in through the top. Okay, and that in through the top is, this is just the mass flow rate in through the top right here. That's this term. And so then we have our linear momentum equation that we can simplify. We just go through a few steps here to simplify it down. You'll notice here we have this pressure gradient, dpdx, and dpdx we can put in terms of the velocity by using Bernoulli's equation. Now Bernoulli's equation can't be used inside the boundary layer because there's viscous stresses there, but it can be used outside the boundary layer because that's an outer, essentially inviscid flow. So we can use Bernoulli's equation outside the boundary layer to get what the pressure is. And so the pressure can be found this way outside the boundary layer. Remember, the velocity outside the boundary layer is capital U. That's just the outer flow velocity. And if you take the derivative of this, you get dpdx right here, and that dpdx will just substitute in right up there. And if you do that and a little more rearranging, you'll end up with what's known as the Karman momentum integral equation right here. So just to kind of, again, you don't need to know all the details of that derivation. I just kind of quickly stepped you through it just so you can see how it was done. But it uses linear momentum, conservation of mass, and Bernoulli's equation. And what we did is we just analyzed a small section of small section of a boundary layer. Okay, so this expression that we have here, the Karman momentum integral equation, just relates quantities in the boundary layer. So that's the, when I talk about this method being semi-empirical, this is the analytical or the theoretical part of it. It doesn't have any of the experimental part just yet. Okay, so this expression holds true given the, the assumptions that we went through, like a steady flow and things like that through our derivation, incompressible, what have you. So here's the Karman momentum integral equation. You can see the wall shear stress, the momentum thickness, the displacement thickness, and then the outer flow velocities are the capital U's. Okay, so the way we use the Karman momentum integral equation is in this equation we substitute experimental data. So again, the whole purpose of this equation is to deal with boundary layers that aren't laminar or don't satisfy the assumptions going into the Blasius solution. So we'll use this to derive relations for a turbulent boundary layer. We could also use it to derive expressions for boundary layers over curved surfaces where there'd be a pressure gradient. So we can use it. It's a much more general technique, but it relies a little bit on experiments along with the derivation we just did to get this Karman momentum integral equation. So let me just describe for you how this works, and then in separate videos we'll go through examples where we actually apply it. So how it works is this. Step one would be we approximate what the velocity profile looks like in the boundary layer. So approximate the velocity profile, and I'll just write it in dimensionless terms within the boundary layer. So remember, our boundary layer looks something, our velocity profile looks something like this. So let me put this in dimensionless terms. This will be y over delta. This will be our value of 1. And then down here, this will be u, little u over capital U, and that'll be a value of 1. So at the 99th percentile value for the boundary layer, then little u over capital U is equal to 1. Clean that up a little bit. Okay, so this is kind of, if you went out in the laboratory and you made some measurements of the velocity profile in the boundary layer, it might look something like this. And then what we'll do is we'll just approximate what that curve is. Maybe it looks like a parabola, maybe part of a sine wave, maybe a cubic kind of equation. But you just do a curve fit to that data, okay? And then that's what you use here, is just your approximation to it. Okay, just a curve fit. So that's the empirical part of the analysis. So once we have that, then the second step, number 2, is we can determine the displacement thickness and the momentum thickness using the equation from step 1, and then these will be as functions of the 99% boundary layer thickness. So the idea is this. Let's just do the displacement thickness. We have the displacement thickness is just from 0 to delta of 1 minus little u over capital U dy. So we can substitute in for little u over capital U, that's this thing right up here. We can substitute in there, evaluate that integral, and then you'll see that the displacement thickness will be a function of delta. So that's what I mean by that. And we can do the same thing with the momentum thickness, right? We can substitute our curve fit in to our expression for the momentum thickness and then get that also as a function of the 99% boundary layer thickness. So that's step 2. And then once we have that, the reason I want to do that is you can see that they show up here. Okay. Step 3 is we'll calculate what the wall shear stress is using our curve fit. Okay, so what we'll do is we'll determine our wall shear stress up here using this equation. So, for example, for like a laminar flow, we know, well, we just know in general that the wall shear stress will be mu times du dy evaluated when y is equal to 0. That's the wall shear stress. It's just our standard Newtonian method for calculating shear stress. And we're specifically evaluating it at the wall, so we want it when y is equal to 0. So what we'll do is we'll just substitute again. Let me do this in a different color. We'll substitute this expression up here down into there, and then we can evaluate what that wall shear stress is. And again, you'll get an expression for the wall shear stress will be some function of delta when you do that. Okay, so you'll get that in terms of delta. So now what you'll see is that we have, and by the way, we can either use this kind of behavior, just this kind of expression, or in some cases actually people use experimental data. They actually measure the wall shear stress and use that experimental data as well. So that's another way to do it. But now what you see is that we have our wall shear stress in terms of delta, and our delta M and delta D also in terms of delta. And then the capital U is still just our outer flow velocity. If we're dealing with a no pressure gradient, then the capital U would just be a constant, because from Bernoulli's equation up here, you can see if the pressure gradient is 0, then the capital U has to be a constant, because du over dx would have to be 0. So that means U is a constant. If U is a function of x, then what we would do is put in just U as a function of x here. If the outer flow velocity was changing with the x direction, we would just explicitly put that function in here. So what you'll see then is this Karman momentum integral equation, when you substitute in for our displacement momentum thickness and our wall shear stress, it'll all be in terms of delta, the 99% thickness, as well as x. Because again, if I substitute in for u, if it varies in the outer flow velocity, it'll be a function of x. If it's a constant, it's just a constant. So this whole equation will be in terms of delta and x. So step 4 is substitute into the Karman momentum integral equation. That has to be true. That just comes from linear momentum, conservation of mass, and Bernoulli's equation. And then what you'll end up with is an ODE in terms of delta and x. And then you can solve that you can solve that ODE then. So it's an ordinary differential equation. You need to have some boundary conditions on it. The boundary condition that you'll get, that you should use, is the delta when x is equal to 0 is just 0. Just that kind of goes with this idea of this, that if you've got kind of an outer flow an incoming flow that's nice and uniform when it hits. It's just that the boundary layer thickness right at the, when x is equal to 0, the boundary layer thickness is 0. So that's what we normally use as a boundary condition. You don't have to do that. If you're analyzing some other special situation, you could change that boundary condition. But normally this is what we use. Boundary layer thickness is 0, right where the boundary layer starts. So then you can solve that ODE. So solve the ODE with the boundary condition to get the boundary layer thickness as a function of x. And then once you have that, you can find your displacement thickness, your momentum thickness. You can get the wall shear stress. You could get the friction coefficient, and you can get a drag coefficient. You can get whatever it is you're interested in after that. The key is to get this 99% thickness as a function of x, and then once you have that, you can find all these other things pretty easily. Okay, just from their definitions. You just go straight from their definitions. So that's the general procedure for using the Karman momentum integral equation. So it relies on some theoretical aspects to get the actual equation. So again, that's just linear momentum, conservation of mass, Bernoulli's equation. So that's the analytical part. And then the empirical part, the experimental part, is where we approximate what the velocity profile looks like. And then from that, we basically evaluate some of the quantities in here and then solve a differential equation to get what the boundary layer thickness should be. Okay, so that's the empirical part. And we use this technique again in order for us to figure out expressions for turbulent boundary layers or boundary layers with some sort of pressure gradient, or where the outer flow velocity isn't a constant, that it varies. And so that's how we use this equation. So we'll use it specifically in this course to get the turbulent boundary layer expressions. But I give a couple of examples in separate videos where I actually apply this a few different ways. I think we look at a parabolic kind of velocity profile as an approximation to a laminar boundary layer, just to kind of check to see how close we get to the real Blasius solution. I think I also do it with a sine wave. And then there's at least one other example. So you might want to take a look at those to see how we apply this equation. Hi, I'm just tacking this on to the end of this Karman momentum integral equation video lecture because I realized I forgot to tell you something. When you're writing down your empirical expression for the velocity profile in the boundary layer, you need to satisfy certain boundary conditions. So if you take a look at the screen here, what I'm talking about is when we write down this function for the velocity profile in the boundary layer, recall that we're trying to get what the velocity is, the horizontal velocity. Here it's expressed in dimensionless form as a function of the dimensionless vertical position. We need to make sure we satisfy certain boundary conditions. The first one is, of course, the no-slip boundary condition at y over delta equals 0. This is right at the plate surface, so we should have 0 velocity there. And then the other one is that we match the outer flow velocity when y over delta is equal to 1. So just kind of sketching this out, here's our u over capital U, here's our y over delta, and we need to make sure it's 0 when y over delta is 0, so that's this first boundary condition. The second one is when we reach the edge of the boundary layer, we need to make sure that we match the outer flow velocity profile. So we want to have something kind of like this. Right, so here's our velocity profile. So this boundary condition is the one here. This boundary condition is the one there. So you need to make sure that your function satisfies those two boundary conditions for sure. Now there are other boundary conditions depending on the complexity of your function. If you have more complex functions, then the way that you want to, the additional boundary conditions you want to have are to make the profile smooth right at this junction here. So this boundary condition right here makes it continuous, but then you also want to make it smooth so that the slope there is continuous. So that one would be the following. Oops, I should write this as a slope. So this boundary condition would make it smooth at this point. So let me show you the difference between continuous and smooth. So here I'm going to sketch out a continuous but not smooth profile. So one that's kind of piecewise continuous there. That's a continuous boundary layer that would satisfy these two, and that would be perfectly fine if this is the empirical expression you'd want to use. If you want one that's maybe a little better, then you'd have one that's smooth, which would look like this. One that comes up here and then smoothly transitions into the outer flow velocity. So here the slope is continuous right at that point. The gradient, I should say, is continuous. That the horizontal velocity does not change with respect to vertical position right at the point 1, 1. So this kind of boundary condition would be an extra one if you have a more complex profile. Okay, so, and then you could continue this idea. You could look at the curvature, which would be the second derivative rather than the first derivative, and then so on and so forth. The more complex your function is, then you can have additional boundary conditions that do a better job of matching to the outer flow velocity. So just to recap, when you write down your empirical expression for the velocity profile in the boundary layer, you just need to make sure you satisfy at least these two boundary conditions. No slip at the plate surface, and that it's continuous with the outer flow velocity. And then if your function here is of higher order, meaning you have some additional terms, then what you'll want to do is start matching these, like the gradient term. So you want it smooth at that interface, and then if you have even more complex expressions, then you might want to match the curvature and so on. Okay, so sorry I had to tack that on to the end, but I forgot to put it in the original lecture. All right, so we'll go ahead and end it there.